Hello everyone, my name is Ruben and I'll be presenting a measurable additive function. An additive function is a function that satisfies the equation f of x plus y equals f of x plus f of y. We can think of f as getting distributed onto the addition of x and y. Now this might not seem as that interesting of a topic, but it actually combines many elements learned in classical analysis in a unique way. What we'll show today is that when a function is additive and measurable, it is also linear. We'll end with an example of a function that is additive but not measurable. So before talking about the measurable additive function, we're going to start with a lemma called the Steinhaus theorem. Now what the Steinhaus theorem tells us is that if we have a measurable set E with positive measure, and we define this set E star, which is the set of all x minus y such that x and y are in E, then there exists an alpha that is positive such that there's an sort of this symmetric and open interval of minus alpha alpha that is included in E star. Okay, and we'll prove this. So E is a measurable set, so we're going to make it contain a closed set C, right? Also of positive measure. We know that this closed set exists. And we'll assume that C is bounded as well. And then we'll take an open set, such that E is inside of O. So we can think E as being sandwiched between O and C. O being an open set in the outside, and C being a closed set in the inside. C being bounded as well. So E is measurable, right? So we can take any epsilon greater than 0 and estimate the measure of O minus C, right? Now we know that, again, E is measurable, so we can arbitrarily approximate it from the outside by open sets and by the inside by closed sets. So what I can do is I can sort of add and subtract an E here, right? That's what I did. I'm not actually adding and subtracting an E, right? These are sets, they're not numbers, but we can kind of think about this, right? Because O minus C is O minus E plus, right, union E minus C. And because of the subadditivity of measure, this is smaller or equal in the measure of O minus E plus the measure of E minus C. Now, because I can arbitrarily approximate E by open sets and closed sets, I can make O minus E and E minus C smaller, strictly smaller than epsilon over 2 plus epsilon over 2 to make this smaller than epsilon. Now, I said that the closed set inside was of positive measure, and E is an arbitrary positive, and epsilon is an arbitrary positive number. So I can just set epsilon to be the measure of C. And so we'd made the measure of O minus C strictly smaller than the measure of C. And we'll actually need this for later. What we'll also do is we'll introduce a function between two sets A and B. This function is called d of AB, which is the infimum of all the moduluses of x minus y, such that x is in A and y is in B. And also I'll make A and B disjoint. This sometimes is referred to as the distance between the sets A and B. Now, it's not to be mistaken with a metric, right? This is not a metric at all. But we can sort of think of this as the shortest distance between A and B, right? Because we know the modulus of x minus y is literally the distance between x and y on the real line. And so if we take all the x's and a's and all the y's and b's and they're disjoint, we take the infimum of all the small distances, we can think of this as being the smallest distance between the sets A and B. Now, if we take A to be C and B to be O complement, right, where C is the closed set inside of E and O is the open set sort of outside of E, the distance between C and O complement is actually strictly positive because C and O complement are disjoint. Now, the reason why C and O complement are disjoint is rather intuitive, right? Because C is inside of E, right? C is a closed set inside of E, and E is inside of O. So the complement of O has nothing to do with E, let alone C, right? So their intersection is obviously going to be empty. So this part is really intuitive, but the fact that the distance between C and O complement is strictly positive is actually maybe not that intuitive. So we're going to explain it. So a way to explain this is we'll actually assume it to be 0, right? Because this number can only be equal to 0 or positive because of the modulus. So we'll actually assume this to be 0, which is equivalent of saying that the infimum of all the x minus y's such that x is in C and y is in O complement is equal to 0, because that's the definition of this. And so what does this mean? Well, now we're going to use a definition of the infimum, right? But I'll use it with sequences. So I'm going to choose a sequence in C and another sequence in O complement such that for any epsilon greater than 0, we can make the difference between the two sequences arbitrarily small, right? That is literally the definition of an infimum, but I'm using sequences right now. Now, C is compact. Here I just wrote it like that, but we have to justify why, right? So C is closed and bounded, and we're working in the real line. So using the Hein-Borel theorem, we can then conclude that C is compact. This obviously doesn't work in general metric spaces, but here we can use this because we're working in the real line. So C is compact, so we know that this xn here, the sequence that I chose inside of C, has a convergent subsequence as xnk, right? That is the definition of a compact space. That's how we define it sometimes. And so there exists some x in C, right, such that for all epsilon greater than 0, we have this convergent subsequence, right? So we have x and k that converges to x, otherwise known as making the difference between x and k and x arbitrarily small. And so now what I'm going to do is I'm going to take the sequence that I chose inside of O complement, yn, and I'm going to extract the subsequence of it, ynk, and I'm going to estimate the difference between y and k and x. So subtracting and adding an x and k and using a little triangle inequality, I can actually estimate this to be smaller than epsilon, right? Because y and k and x and k are two sequences, and I know that any two sequences, x and k is a sequence in C, and y and k is a sequence in O complement. And so since the infimum is 0, as I previously justified, this could be made strictly smaller than epsilon over 2. And here I use the fact that C is compact, right? So x and k converge to x, as I justified here. And so I can make this arbitrarily small. So we can actually say that y and k converges to x. Now y and k is a subsequence of yn, which is a set inside of O complement. Now O complement is a closed set, right? Because O is open and the complement of an open set is closed. And so I know that since y and k is in O complement, x has to be in O complement because, again, it's a closed set, right? It has to contain all of its limit points. However, I said that x was in C, right? And C intersection O complement is empty, right? They're disjoint. So we actually have a contradiction because x can't be in two places at the same time if they're disjoint, right? So the distance can't be 0. And so we showed that the distance between C and O complement has to be strictly positive. Now we're actually going to use this as our alpha, right? If we remember in the definition of the Steinhaus theorem, right, we wanted an alpha greater than 0. So we'll actually pick alpha to be the distance between C and O complement. And we're going to let x be an arbitrary real number inside of minus alpha and alpha inside of this interval. And so obviously what we want to show later is we want to show that x is an E star too, right? To show that this is a subset of E star. So x being in minus alpha alpha means that the absolute value of x, or the modulus of x, is strictly smaller than alpha. And so we always have that C minus x, the set, is included in O, and that obviously E is sandwiched between C and O. Now this is obvious. The reason for C minus x to be inside of O, this is also intuitive if you think about it. So C is inside of E, right? It's a closed and bounded set, a compact set inside of E. And so because the distance between C and O complement, strictly positive, is equal to alpha, and x is somewhere in this interval, then if you shift C to the left or to the right, you're never going to really get out of O because alpha is, again, the distance between C and O complement. So this set actually always has to stay inside of O. And so we will show that the intersection between C and C minus x is not empty. We're going to see why this is important after I finish this proof. Once we show this, the proof is basically done. So we're going to start with the fact that C is included in O, right? This follows from this. And now we're just going to do some standard set and measure theory. So we're going to intersect C minus x complement on both sides. And because the measure is monotonic, we know that the measure of C intersection C minus x complement is smaller or equal than the measure of O intersection C minus x complement. And this is just a set subtraction, right? It's O minus C minus x. And because C minus x is inside of O, we can then transform the set difference into a difference of two measures. And the measure of C minus x is actually just equal to the measure of C. Then putting this back in, because C is inside of O, I can make this equal to the measure of O minus C. And because of our first result that we proved, we showed that the measure of O minus C is strictly smaller than the measure of C. And so we have this inequality here. And we know that C minus x is measurable because C is measurable, right? And remember that the Lebesgue measure is translation invariant, right? So the measure of C can be written as the measure of C intersection C minus x plus the measure of C intersection C minus x complement. We showed that this is strictly smaller than the measure of c. So canceling the measure of c on both sides, we then have that the measure of c intersection c minus x is greater than 0. And so this and this are measurable sets, so the intersection is measurable. And so since the measure of, this measurable set is strictly positive, we know that the intersection isn't empty, right? There has to be some values there that are contributing to this positive measure. And so the intersection is then not empty. Then, for some x and minus alpha alpha, we can then find some two arbitrary numbers in C, right? Because their intersection is not empty, such that y, right, is equal to z minus x, right? Because their intersection is not empty, you can find sort of these two values that equate to each other, two arbitrary values of C. And so juggling the x around and the y here, we have x is equal to z minus y. Right? But y and z are in C, and C is a subset of E. So then we can say that y and z are in E. And so x is equal to z minus y, so that y and z are in E. But this set is literally E star, right? That's how we defined it. And so x is in E star. So we prove that if x is in the open interval minus alpha alpha, x is also in E star. And so we just proved the Steinhaus theorem, right? That minus alpha alpha is a subset of E star. Okay, so now for the main dish. Now we're going to talk about the measurable additive function. Okay, so we're going to consider a function going from the reals to the extended reals, meaning that we can actually accept infinite values, right? Like infinity and minus infinity. And so for all x, y, and r, we have this equation, f of x plus y is equal to f of x plus f of y, right? This is an additive function, right? Now we have that f is also measurable. So there's these two propositions here, that f is either finite or infinite. And that if f is finite and measurable, right, then for all x and r, we have that f of x is equal to x f of 1, right? This states that f is linear, right? Because f of 1 is just a constant, right? So this is just like c times x, just a constant times x, right? That is if f is finite and measurable. So we're going to prove these two statements. Actually, the first one is very immediate, right? So if f is infinite, then f of x plus y is also infinite for all y, right? So yeah, the first one is pretty simple. The second one is a bit more involved, okay? And we're going to do this step by step, okay? To not confuse anyone. Okay, so to start, we're going to consider all the natural numbers, okay? So for all n in the naturals, okay? So we see that if we take f of x plus x plus x plus x n times, right? X plus x plus x n times, right? This is just n times x, right? By definition of multiplying a number by a constant, right? But also we can use the additive property of f to distribute f among this addition, and we're actually adding f n times, right? Because there's n x's. And so we have here that f of nx is equal to n times f of x. So we showed that f of nx is equal to n f of x, so we can sort of pull out this n for natural n, right? Now, obviously, this is not enough because we need, n to be real, or this constant to be pulled out to be real, but in due time. Okay, so now we're going to consider an integer, right? M to be an integer, okay, which is sort of the next step. But before that, because the integers, we need negative numbers for this, we need a trick to actually show that we can work with negative numbers here. So first we're going to consider f of x plus 0, and that's just f of x plus f of 0, right? Using, again, the additive property of f. But x plus 0 is just x, right? So this is just f of x equals f of x plus f of 0, and canceling f of x on both sides, we have that f of 0 equals 0. So f passes by the origin. Right, and using this, we can then consider f of x minus x. X minus x is 0, so f of x minus x is f of 0, and we just show that this is equal to 0. However, again, using the additive property of f, we can distribute f on this, and this is just equal to f of x plus f of minus x. And so putting f of x on the other side, we have that f of minus x equals minus f of x. And this actually also shows that f, right, it's an odd function, right? And so, if n is part of the naturals, f of minus nx, right, first we can take out the n, because n is a natural number, we just showed this, right, and f of minus x, because we just showed that f is an odd function, we can take out this minus, And so f of minus nx is minus nf of x. And so since n is a natural number, we just accepted the fact that f of minus nx is minus n times f of x. So we assumed, right, n was a natural number. And so now we're assuming all positive and negative natural numbers, right? But that's just the integers. So f of mx is mf of x for all m in the integers. So we have the natural numbers and we have the integers. So those are the two sort of ingredients to make a rational number, right? So now we're going to consider the rational numbers. And we know that if this is true for rational numbers, we know that this is a good thing because the rational numbers is a very nice set in the real numbers. So maybe we can do something with this later. Actually, not maybe, we will, but would like to keep an element of suspense or something. Okay, so now we're going to consider f of x, and I'm going to do this trick here that I'm going to multiply the top and the bottom by n, a natural number. And so nx, again, what's nx? It's x plus x plus x sort of added to each other n times. And so we're going to sort of split this fraction n amount of times. So I'm going to put an n here, right? Have this f of x over n plus f of x over n plus f of x over n. And I'm going to distribute the f again using the additive property of f, and this is just f of x over n plus f of x over n plus f of x over n times. So this is n times f of x over n. And so dividing both sides by n, we have that 1 over n times f of x is equal to f of x over n. So we actually managed to pull out a 1 over n, right? So we actually even allow fractions. So we have all the ingredients we need for a rational, right? So if we let r equals m over n to be sort of this arbitrary rational number, and here I actually assume that the natural numbers start at 1, so I'm not going to have any issues dividing by 0. So m is an integer and n is a natural number. We have that f of m over n, right? Because m is an integer, right? We showed that we can pull out the m, and we just showed here, like a second ago, that we can pull out the 1 over n. So this is just m over n times f of x. And we know that m over n is our rational number r, so f of r of x is equal to r times f of x for rational r. Rational r. And so in particular, if x equals 1, right, f of r is equal to r times f of 1 for all r in q. So we showed the equation is true, right? The linearity of the equation is true for rational r, right? But now we want to show that it's true for all real numbers. But before that, we're going to consider, right, we remember that f is finite and measurable. So we can find these measurable sets e1, e2, and e in a real number m such that e1, right, this set is measurable, right? That's the definition of a measurable function, the set of all x's such that f of x is strictly smaller than m, and the set of all x's is such that f of x is greater than minus m. And if we intersect these two, this is just the set of x that the modulus of f of x is strictly smaller than m, and this set is measurable and of positive measure, right? Because f is finite, so we can always bound, so f can always be bounded on a set of positive measure, which is e. So we found a measurable set e with positive measure such that the modulus of f of x is strictly smaller than m on e. Okay, so now we're going to let z be part of e star. Okay, we remember that e star is the set of all values in e such that if x and y are in e, x minus y is in e star. So then z is equal to x minus y for some x, y, and e. So the modulus of f of z, which is f of x minus y by definition, right, using the additive property of f, this is just f of x minus f of y. And so because we know, and this is, using the triangle inequality here, we have that the modulus of f of x minus f of y is smaller or equal than the modulus of f of x plus the modulus of f of y. And because we're in this measurable set e, and we know that f is bounded on e, we know that the modulus of f of x is smaller than m, and the modulus of f of y is smaller than m, and so the modulus of f of z is then strictly smaller than 2m. But we know that e star contains an interval minus alpha alpha, right, for some alpha greater than 0. And so if the modulus of z, right, because z is in e star, so the modulus of z is smaller, strictly smaller, we can make the modulus of z strictly smaller than alpha over n. And this is always going to be strictly smaller than alpha, right, because n is a natural number here. And so we know that z will always be in e star. So multiplying both sides by n, we know that the modulus of n times z is then strictly smaller than alpha. And so nz is part of minus alpha alpha, which is a subset of e star. And so nz is an e star. And so we know that the modulus of f of nz has to then be strictly smaller than 2m by what we just showed. And so here, using the property that f we can pull out this n here, because n is a natural number. We can then pull it out of the function and divide it. And so now we show that the modulus of f of z is actually strictly smaller than 2m over n for all natural n. Okay, so now we're almost done. What we're going to do is we're going to pick an arbitrary real number. Well, that is in the measurable set E, but now it's just any real number, and a rational number q. And so because, right, the rationals are dense in the reals, right, that is why we prove this property of the rational numbers, right, that it's a really nice property because they're dense in the reals. We can always find an alpha greater than 0 such that the distance between the this real number and this rational number can be made arbitrarily small, right, and n can be made as big as we want, and alpha is just this positive number. And so now the grand finale, we're going to consider the difference, the absolute value of the difference of f of x minus x f of 1, where x is a real number. What I'm going to do is I'm going to subtract and add an f of r. And so here I'm going to use the property of this f of r, where r is rational, that I can actually pull out the r. And so this is equal to r times f of 1. I can factor an f of 1 here, and then make this addition be smaller or equal than the absolute value of f of x minus r plus the absolute value of r minus x times f of 1. And so I'm going to make both of these arbitrarily small. So x and r, right, they're in E, x being a real number, r being a rational number, and E being that measurable set that f is in, defined on. And so r minus x is part of E star, right? So we know that f, because x and r and E and r minus x is in E star, I know that f of x minus r can then be strictly smaller than 2m over n using the property that we showed. And f of 1 being a constant can be pulled down because r minus x is in E star. We know that we can make it arbitrarily small. Actually, not because r minus x is in E star. That's just because r is a rational number and it's dense in the real. So we know that we can make this difference arbitrarily small, right? Because of what we showed in the previous slide. And so we know that we can make this arbitrarily small, right? Because we can make n go to infinity. And so what's the only number that can be made arbitrarily smaller than any positive number? Well, it's 0, right? So f of x minus x f of 1 is 0, right? This is fixed. And so this means that f of x is equal to x times f of 1 for all x in real. And so this shows that f is linear. Okay, so like a classical analysis situation here, we're going to consider a non-measurable solution to this equation. So we're going to completely destroy all the nice things we did and consider a really messy solution. So we're going to consider the real numbers as a vector space over the field of rational numbers. And we can do this, right? Because, again, the rational numbers form a field. And we have to be comfortable in assuming that every vector space has a basis. And so we're going to consider Hamel bases for the real numbers over the field of rational numbers. And so for all x and r, we're going to consider a set of real numbers y alpha such that x can be written as a linear combination of the elements of the set, where obviously all the scalars are rational numbers because we're working over the field of rationals. And so since the rational numbers are countable and, well, the reals are uncountable, then there are actually uncountably many of these bases, right? And so there has to exist a Hamel basis, right, r alpha, where alpha is in some set, containing some rational number r. And so since it contains the rational number r, it implies that it's a maximum linearly independent family of elements of r over the field of rationals, and that r is part of this set, right? And so now I'm going to pick the beta in the set A, such that r beta is r, and we're going to consider the subspace V of r generated by the set of r alpha, such that alpha is part of A except for this little index beta, right? And so now we see clearly that V and Q, their intersection is only 0 because they're both subspaces, and R then forms a direct sum between V and Q. In particular, for any x and r, we have the intersection. The cardinality of the intersection of V and x plus Q is then 1 because their intersection is just 0. And so it follows that V is a Vitali subset of R because it contains one element from each equivalence class of x plus Q, right, as stated in this equation. And so for all x and r, because r is a direct sum between v and q, we have the unique representation x equals v plus q, where v is in v and q is in the rationals. So now we're going to consider the function f goes from r to r, defined by f of x equals q, where q is a rational and x is a real number. And so now we can show that f is additive, right? We have these two representations of real numbers, x1 equals v1 plus q1, and x2 equals v2 plus q2, where v1, v2 are in the Vitali set, subset of R, and q1, q2 are in the rationals. And so, performing this calculation, moving things around, we see that f of x1 plus x2 is actually equal to f of x1 plus f of x2. However, if we consider the kernel of f, right, if we consider all the values of f, such that f of x equals to 0, right, all the q's have to be 0. And so that's just the Vitali set, right? That's just v, right? That's just, this q1 and this q2 are just 0, right? So that's just x equal to v. However, this set is not measurable, right? V, the Vitali set, is, right, the most well-known example of a non-measurable set. We proved this, I think, in class, right? And so, since this set is not measurable, f is non-measurable. And so we have a non-measurable additive function, right? And so that's it for my presentation. I hope you guys liked it, and